So today we are going to be talking about the natural response of first order circuits. And if you watch the pre-recorded lecture content, you should be at least vaguely aware that it's roughly the exact same thing that we did last Friday. The only real difference is that the sources are no longer being taken out of the circuit, or they're no longer being turned off to stop their influence on our energy storage elements. Instead, they're being either added in or left in so that our response at t is equal to infinity is no longer zero. So with that in mind, let's go ahead and take a look at our in-class assignment. So in this first problem, maybe I should actually zoom out a little bit so we can see the whole thing. So in this first problem, when that switch closes at t is equal to 0, it's actually adding in this left 12-volt source, this guy right here. In addition to that, this 12-volt source, excuse me, is completely unaffected by the switch opening or closing. So it's going to influence the behavior of the inductor always. So this is definitely not a natural response problem because there are sources left in after the switch has closed. So the only real changes that we're going to need to make to our analysis, excuse me, goodness, are to analyze the circuit at t is equal to infinity as well. And hopefully you guys watched the video lecture, so you saw my little bit of content on the concept of a time constant. And so we're going to be using this generic form for our overall answer. Y of t is equal to y at 0 minus for t less than 0 minus. That bit stays exactly the same. But for t greater than or equal to 0 minus, we're now going to have y of 0 plus minus y at infinity, e to the minus t over tau. And the reasons why we have to modify our expression are all covered in the lecture material. Effectively, it's just to make sure everything stays continuous when that's applicable. And tau is our time constant, which is L over R for RL circuits, and R multiplied by C for RC circuits. So we now have one generic expression for everything. All right, so with that in mind, let's analyze this circuit at t is equal to 0 minus. How much room do I have here? Not a whole heck of a lot. So let's look at it on the left-hand side of the screen. So at t is equal to 0 minus, that switch is open. So this 12-volt source isn't actually doing anything. So I'm just going to conveniently not draw it. So what we should have is our middle 12-volt source connected to a 2 ohm resistor. Here's our 4 ohm resistor. Here's another 2 ohm resistor. And our inductor is going to look like what? At t is equal to 0 minus.
Short circuit.
Short circuit. So what effect does that short circuit have on the 4 ohm resistor? Let's start there.
It's basically like it doesn't exist. It's just shorted.
Yeah, so the 4 ohm resistor is in parallel with the short circuit, so we know that no current will be able to flow through this path. So here is IL at 0 minus, and here is VR at 0 minus, and I'm going to make a little table over here. So let's see. IL at 0 minus, VR at 0 minus. So can anybody tell me what either of these two quantities are going to be? Let's start there. Apply simple circuit analysis techniques and tell me either what the inductor current is at t is equal to 0 minus, or the resistor voltage is at that same time.
Should be 3 amps, right? Because those two resistors are in series. Then you just divide the 12 by the 4 and you get 3 amps.
That's exactly correct. So since all the current will skip past the 4 ohm resistor, the 12 volt source sees this 2 ohm resistor in series with this 2 ohm resistor, and then we can just apply Ohm's law. So 12 volts divided by 4 ohms is exactly 3 amps. What does that tell us about the resistor voltage VR at 0 minus?
It would be 6 volts.
6 volts using Ohm's law again. 3 amps multiplied by 2 ohms gives us 6 volts. So nothing particularly crazy there. Is everybody okay with my analysis at t is equal to 0 minus? All right, nobody's saying they're not, so let's jump ahead. At t is equal to 0 plus, our switch is now closed, right? So we're going to have a circuit that looks like this. What am I going to do with my inductor in this case? This is at t is equal to 0 plus.
We're going to treat it like a current source with the current of IL at 0 minus.
All right, so current source, same direction as IL and same magnitude as IL. So IL is defined from left to right with a magnitude of 3 amps at t is equal to 0 minus. So that's why I've replaced the inductor with a 3 amp current source, direction left to right. So here is our voltage VR at 0 plus. We know for a fact that IL at 0 plus has to continue being 3 amps. How are we going to figure out what VR at 0 plus is?
It should be the same thing.
So I would argue that our circuit has changed significantly enough to where we cannot guarantee that 3 amps of current is flowing through that rightmost 2 ohm resistor.
Would it be best to use nodal?
So we could do nodal analysis. So let's see, if we did nodal analysis, we have a node here that has a known voltage of 12 volts. We have a node here that has a known voltage of 12 volts. And we have a node here that has an unknown voltage. And let's say, for argument's sake, that I'm going to make the bottom my reference. Does that seem reasonable to you guys if we were going to use nodal analysis there?
Yes, sir.
All right, so the only unknown voltage then is this guy VR, right? Because VR at 0 plus is the potential difference between this node and our ground. So this nodal voltage exactly represents the voltage I'm trying to find. We good there? So from this, I'm going to just apply KCL at this rightmost node. And I can see, since currents that are exiting are positive, I will have negative 3 amps plus VR minus 12 volts over 4 ohms. So that's the current directed from right to left through the 4 ohm resistor, plus VR over 2 ohms is equal to 0. One equation, one unknown. We should be able to solve that reasonably quickly. So that's going to be 1/4 plus 1/2 VR is equal to 3 plus 12 over 4. If my algebra is right. So let's see. There's where the factor of 1/4 came from. There's where the factor of 1/2 came from. I moved my 3 over and I'm moving my 12 over 4 over. Okay. So 0.75x equals 3 plus 3, 6. So VR looks like it's 8 volts now. Did anyone else get a similar result?
Yes, sir.
Yes, sir.
All righty. So finally, we have our circuit analysis at t is equal to infinity. So what's going to change in our circuit that we have drawn on the screen right now at t is equal to 0 plus? What's the only change that we're going to make to have it be valid for t at infinity?
The inductor is going to be a short again, but with the unknown current.
Right, the inductor is going to be a short circuit again because at t is equal to infinity, we are at DC steady state again. So here is our current IL at infinity. Here is our voltage VR at infinity. And again, this 4 ohm resistor here gets shorted out. So how would you guys suggest I solve for either IL at infinity or VR at infinity? And what I'm going to do to make things very clear, I'm going to go ahead and just erase that 4 ohm resistor so that we don't accidentally include it in anything. We know the current flowing through it is 0, which means the voltage drop over at 0. So it's doing nothing for us being in the circuit except offering us a place to potentially make a mistake. Anybody have any ideas?
Mesh looks pretty good since there's only 2 meshes.
So mesh is possible, but I feel strongly that in this case it will be overkill. And let me explain what I mean by that. This is a node, right? Let me exaggerate the node. Do it like we would have done on maybe the first day of class. And we have a second node here. And we have a third node.
So is VR just 12 volts?
That is exactly what I'm getting at, yes.
Okay, I
The
see.
potential difference between the orange node and the blue node is 12 volts, which is the exact same thing as the voltage drop over that 2 ohm resistor. So we can see effectively by inspection that VR should be 12 volts. Everybody okay with that?
Yes, sir.
So does that in any way, shape, or form help us determine our inductor current IL at infinity?
Yeah, because we can just use Ohm's law at this point.
Yeah, the inductor current is going to flow down through that 2 ohm resistor over which VR is labeled. So Ohm's law tells us then that I at infinity is 12 volts divided by 2 ohms. should be 6 amps. So we now have all of the information that we need to plug into our generic equation. So the answers are right here. So I guess, oh, actually, let's calculate the time constant. We do need that. So the time constant is going to be gained by looking at our circuit as a dead network during the transient condition. Okay, so to be very clear about what I mean about that, the only time we can't look at it to determine the equivalent inductance and equivalent resistance is t is equal to 0 minus, because that's before the transient occurred. So if we look at our circuit at t is equal to 0 plus, where we take our inductor out and look in through here, we need to make sure that we're looking at a dead network as well. And our 4 ohm resistor still exists. So what would the equivalent resistance seen be looking into this network? And we don't need this guy right here, right? So to be clear, I've closed this switch because we're looking at it during the transient condition. I've zeroed out both of my voltage sources because I need to be looking at a dead network. And I've taken my inductor out and I'm looking in through the terminals where the inductor was. So how am I going to figure out what the equivalent resistance is?
It's just going to be that 4 ohm in parallel with that 2 ohm on the right.
4 ohm in parallel with the 2 ohm on the right. Does everybody agree with that sentiment?
Yes, sir.
Okay, I also agree with that sentiment, to make things clear, right? So this 2 ohm resistor here is in parallel with this short circuit, which means that this 2 ohm resistor is effectively doing nothing. So we have 1 node, 2 node. So those guys are in parallel with each other. So 4 in parallel with 2 is what?
H6.
8/6, which is the same as 4/3. Req is equal to 4/3. Leq is simply 2 henries. Sorry, this should be ohms. So tau, because this is an L over R circuit, excuse me, an RL circuit, is L over R. So that's 2 divided by 4/3 is 6/4 is the same as 3/2 of a second. And the inverse of tau is then 2/3 per second. Everybody follow my math there?
Yes, sir.
All right. So now we're not going to actually write things down here. We're just going to check stuff, right? So for IL at t is equal to 0 minus, our answer tells us it's supposed to be 3 amps. That is exactly what we got here. So that seems legit. This guy right here, this -3 is IL at 0 plus minus IL at infinity. IL at 0 plus is 3 minus IL at infinity. 3 minus 6 is -3. So that works out. The inverse of our time constant, we got to be 2/3, which is where this guy comes from. IL at infinity is 6 amps. So it looks like we've gotten the correct, everything we would have needed to put into our generic expression for our inductor current. We can go through the resistor voltage in the same way. This 6 matches this 6. 8 minus 12 gives to this minus 4. The 2/3 comes from the same thing. And the VR at infinity of 12 volts also matches up. So we did everything correctly. So the process that we took for that problem, again, is almost identical to what we did on Friday. The only change is analyzing what's happening in the circuit at t is equal to infinity, because we can no longer safely assume that everything is going to settle to 0 because there are sources in there potentially influencing things. All right, any questions regarding that problem? All righty, let's look at what we have on this guy here. We have a circuit where the switch has been closed for a long time before opening at t is equal to 0. So this is going to be a total response problem as well, because when this switch opens, it does nothing to change the behavior of that 6 milliamp source. All right, so let's work a similar thing here. At t is equal to 0 minus, our circuit is going to look like this. So 0 minus, our switch was closed. Let's see, 10 kiloohms, 2 kiloohms, 4 kiloohms, 6 milliamps. Here's our current IR of 0 minus. What am I going to do with my capacitor?
An open circuit.
Open circuit, exactly right. Plus VC at 0 minus. Alrighty. So we need to figure out what VC at 0 minus is, as well as IR at 0 minus. Does anybody have any ideas on how we might solve for either of those quantities?
For the voltage, wouldn't it be the voltage drop over the 2 kilo ohm plus the voltage drop over the 4 kilo ohm resistors?
So let's write that down. So I'm going to call this V2K and this guy V4K. And you are suggesting that the capacitor voltage is the sum of those two voltage drops over the resistors, and that is absolutely correct. That begs the question, how do we determine either of those voltage drops?
Couldn't you do current division?
Okay. So we can absolutely do current division, and that will give us a great way to figure out what IR at 0 minus is. So applying current division, we have 6 milliamps going up, and it's going to split between the left branch, which contains a total series resistance of 12 kiloohms, and in parallel with that, the right branch, which contains a total series resistance of 4 kiloohms. So to me, that means that I'm going to do 1 over 12 kiloohms here. Like so. Anybody have any questions about my voltage division expression? All right, nobody's saying anything, so I'm going to assume I'm right. So we have 6 milliamps times let's do this. 1/12, 1/12 plus 1/4. 1.5 milliamps. All right. how can we use that information to figure out what, let's say, V2K is?
Ohm's law.
So it'll be the current 1.5 milliamps times the voltage, excuse me, times the resistance 2 kilo ohms. I've intentionally made a mistake here. What is it?
Would it be 12 kilo ohms?
No. Because we're looking for the voltage drop over the 2 kilo ohm resistors explicitly, it will be 2 kilo ohms. The mistake that I've made is that my current is flowing into the negative polarity terminal, and I haven't put in the necessary negative sign. Okay, so since the current is flowing into the negative polarity terminal, I would expect the voltage drop over that resistor to be negative. So it looks like it will be -3 volts. Everybody okay with my line of reasoning there?
Yes, sir.
All right, how do I get the voltage drop over the 4K resistor?
It would be Ohm's law still, but to get the current, you would just do 6 minus 1.5 milliamps.
Okay, so what you're suggesting is that we apply Kirchhoff's current law at this node, and you are absolutely correct that the current flowing to the right is going to be 6 minus 1.5 is 4.5 milliamps multiplied by 4 kilo ohms. It seems like that is 18 volts if my mental math is correct. 16 plus 2 is 18, yeah. So from that, what is VC at 0 minus?
15 volts.
15 volts, just add those two guys together. Alrighty, that seems legit to me. So now let's analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch is opened. That means that guy right there on the right-hand side goes away, and we're going to replace our capacitor with a voltage source that has the same polarity as VC and the same magnitude as VC. And I don't know if we're going to need those guys again, so let's delete those. And this is going to be IR at 0 plus. So VC at 0 plus is 15 volts because the voltage drop over a capacitor cannot change abruptly. What is IR at 0 plus?
Wouldn't it be the same thing?
So you're suggesting that IR at 0 plus will be 1.5 milliamps?
Yes, sir.
All right, let me ask you a question. How are the 10 kilo ohm resistor and the 6 milliamp source electrically connected together?
They're in series, so it's going to be the same current across it.
So yeah, if the 10 kilo ohm resistor and the 6 milliamp source are in series, that means that they have to have the same current flowing through them, which means IR at 0 plus needs to be 6 milliamps. Does that make sense?
Yes, sir.
Yeah. So the only thing that we are ever guaranteed is going to stay the same is the voltage drop over a capacitor and the current flowing through an inductor. We honestly should likely be surprised most times that any resistor quantities stay exactly the same between 0 minus and 0 plus. All right, so we don't need any further circuit analysis there. We were able to do that just using effectively inspection. So what change am I going to make to analyze the circuit at t is equal to infinity?
And change the voltage source to an open circuit again.
That is exactly correct. And I will need to determine VC at infinity and IR at infinity. Can anybody tell me what either of those answers are going to be? Did removing the voltage source that was representing the capacitor at t is equal to 0 plus in any way change the relationship between the current IR and the current flowing through the current source?
No.
No. The 10 kilo ohm resistor is still in series with the 6 milliamp source, so IR must still be 6 milliamps. So how would we go about determining VC at infinity? Let's start by, how did we do it again at t is equal to 0 minus? Let's start there. We said that it was this voltage, V2K, plus this voltage, V4K, right?
Yes, sir.
That relationship does not change. So, do we have enough information to figure out what V4K is by inspection?
Yep.
What is it?
It would wouldn't the voltage just be the same as before, the 15 volts across
What
the,
current is flowing through the 4 kilo ohm resistor?
18 volts.
I'm going to re-ask my question. How much current is flowing through the 4 kilo ohm resistor?
The zero current.
So if there's 0 current flowing through a resistor, what's the voltage drop over the resistor?
0 volts.
All right. How much current is flowing through the 2 kilo ohm resistor?
6 milliamps.
All righty. So is that current flowing into the positive polarity terminal or the negative polarity terminal of the 2 kilo ohm resistor?
Negative.
All right, so using Ohm's law, what's VC at, or what's V2K? Sorry, let's start there.
Negative 12 volts.
All right, so this guy is negative 12 volts. So if we do a KVL loop around this guy, we can see that VC is exactly equal to V2K plus V4K. So that means negative 12 volts plus 0 volts, VC is negative 12 volts. Everybody catching what I'm throwing here?
Yes, sir.
All righty. Okay, what we need to do now is figure out what the time constant is, which is going to require us to know CEQ, which should be pretty easy because there's only one capacitor. So I'm going to go out on a limb here and say that's 150 microfarads. And then we're going to need to determine REQ, and that is the equivalent resistance seen from the perspective of the capacitor. So I've taken the capacitor out and I'm looking in during the transient condition, which means this switch is open. And I also need to be looking at a dead network. So how do I turn off my current source?
And open circuit.
Open circuit. Exactly right. So, what is the equivalent resistance seen by our capacitor?
Would it just be 8 kilo ohms? Sorry, 6 kilo ohms?
Yeah, 6 kilo ohms, 2K plus 4K in series. So from this, our time constant is 150 microfarads times 6 kilo ohms. Which I get to be 0.9 seconds. And the inverse of tau is then, so let's see, that's 9/10, so it should be 10/9 per second. And then we can do a similar thing that we did to verify our answer on problem 1. So VC at 0 minus was 15 volts, that checks out. Then we're going to have 15 minus negative 12, so 15 plus 12 is 27. That checks out. Here's where our tau to the minus 1 came in. VC at infinity was negative 12, so all that checks out. For our resistor current, we had 1.5 milliamps, and then we had 6 milliamps at T is equal to, so this is where things maybe get a little sketchy. Let me explain why this constant value is IR at 0 plus minus IR at infinity e to the minus t over tau plus IR at infinity. So if IR at 0 plus was 6 milliamps and IR at infinity was 6 milliamps, we have 0 multiplied by the exponential function, which is why we're only getting this DC term. Does that make sense? So even though it doesn't look like it's the transient response, it absolutely is. It's just the part that exponentially decays is exactly 0. So everything still matches up. Everything is still hunky-dory with using our generic equation. All right, any questions, any further questions on this problem? Nobody is saying much of anything. That was the last one on the in-class assignment. So do you guys feel comfortable with this, or would you like me to, I don't know, maybe pull an old test problem or something like that and work one more?
I'm fine.
Everybody else okay with calling it a day then?
I'm
Yeah,
good.
I'm fine as well.
I'm good.